it's my pleasure to introduce Marko Stosic. He's a famous mathematician coming far away from Lisbon, so we are very happy to have him here. And he will tell us about Knots-quiver correspondence, this you should know already, but probably you don't know about generalizations and relations to combinatorics, so just 45 minutes and you will know that.
Oh, man.
Or even more, sorry, 1 hour.
Yeah, whatever. So, well, thank you very much. Not sure if I am that famous, but it's a great pleasure to be here in Warsaw with so many friends and collaborators. And it's, of course, a great semester, thanks to Simons and also to everyone participating. So first, although we prepared something, I'm very happy to give a blackboard talk because I think that's the main goal of this semester. And so I'll try to speak. So there will be a lot of stuff, but maybe I'll try to speak about Knots-quivers correspondence. So I'm not sure what was told already here on this semester, but I'll try to say briefly about some details about it, and more about some generalizations that came out recently on maybe the right formulation of this Knots-quivers correspondence. And combinatorics is something which, well, showed up as a byproduct, so it was definitely not our goal, but it's something that, well, at least this part of combinatorics, there is a lot more of something that's completely explicit and very elementary, but that just showed up as a simple side result, but then it gave something which was completely new. So I will just show some things, and well, some things are very recent even. Well, hopefully some things should be online, I hope, very soon, in a couple of days, but I'll come to the end to that. So first I will say something about Knots-quivers correspondence. So of course we need knots and we like them very much, and what originally how it was stated and what we care about are some knot invariants, and in this case we care about, well, polynomial knot invariants, so quantum, let's say quantum polynomial knot invariants as they were calling. So here I know that there is a vast background of people here. So I mean, famously this was started with Jones polynomial, and 80s, let's say 80s, and so these are the knot invariants. So mathematically they are defined for knot projections. So they are you need to use 2D projections of knots to define them. And well, it's still, there is no mathematically rigorous definition as these invariants from 3D objects, for knots in 3D objects. But also they turn out to be, so this polynomial turn out to be related to many stories. So if you want well, formally it's quantum groups, but with SU2, or if you want, that would like SU2 Chern-Simons theory. Compute these invariants. Well, there are many more. Originally it was defined through Lyman algebras and, well, very complicated stuff, or some statistical models, but let's stick to this. And the point, well, the only thing I care about now is that Jones polynomial of a knot is just well, in some variable q, that it is a Laurent polynomial. Important thing is that it has integral coefficients, and that's one of the reasons why these invariants are important, is that it has this integrality property inside. And of course, quickly after that, many, well, I'm not going any details as know about it, but there has been different, well, let's say maybe two different paths of extension of these invariants. So the first one was, so it's related to SL2 or SU2, but also to the representations, and these are, Jones polynomial is famously related to the fundamental representation of these groups. So one goal is, well, let's change. So let's stick still with K family. So you can do this same game with SLN for any n, and one can get, the right letter would be Jn of k. So which would be you do analogous stuff, SLN, it will still be some polynomials. So again, not invariants. SLN polynomials, and famously, so famous long name. You can collect all these. So in this sense, you have here two parameters. One is continuous Q, and one is discrete N. But if it's not that you can rearrange this into a two-variable polynomial, and it's the famous Honfley PT. And luckily, we're here in presence of P, and I hope T is here representative. So there are 8 people in this name. So all these Honfley were more from von Neumann algebras, and luckily PT is, I think, the most important for us because it was using these chain relations and exactly define this polynomial properly. And again, it's a two-variable polynomial, which I'll call QQ. So that if you set if you set A equal Q to the N, it goes to this SLN invariant. So in some sense it collects, okay. So in some sense it collects all of these nice invariants here. So that's one direction of extending it. It was also done quickly, I think a couple of years later. And the other direction is, so here we are like changing group or Lie algebra, and we can change also representations. So we can say, let's look at the other representations. So as I said, so Jones polynomial turned out to be related to SL2 and its fundamental representation, which is two-dimensional representation. But if we think about, so here, let's stick with SL2 and look for, so it's either two-dimensional, you can say R plus 1 dimensional irreducible representations, which can also be seen as R symmetric representations. So R equal 1, meaning two-dimensional representation, it's original Jones. Now I'm a little bit lacking of notation because now we are changing N, but we can change R. So, well, let's try to write it as J SL2, then this symmetric, I'll put SR. And so these, so if this was Jones, so these are famous again, they're colored Jones polynomials. And again, and of course you can double this and go all the way up to here. You can do SLN and any symmetric. So for SLN there are other representations, not just symmetric ones, but for our purposes and for this original Knots-quivers correspondence we care only about symmetric. So and this is again well defined. So J SLN SR of KQ. This is a very general set of invariants. So for any numbers N and R, so I can be also any non-negative integer. We can get these invariants, and this is what we like. So it's not colored Jones, but maybe it's, I don't know if it has any particular name, but like colored SLN invariants. And again, as we did here, so usually you can this as a collection. So this N dependence of SLN, like here for Honfley PT, we can define also something that would be colored Honfley PT, again polynomial. And it's again two variable, but I will put some R showing this representation. So this powers as R symmetric power, and so again that such that A when specified to Q to the N gives SLN R symmetric Jones polynomial. And so more or less that is all, but very rich, again, not so small amount of information that you can get from the SLN, so from A series, so for SLN invariants and any representations. And they are in some sense coded in these polynomials, and maybe try to emphasize a little bit. So, I'm not saying main stars, but maybe main stars of Knots-quivers correspondence, at least how we got there. So, they seem complicated, and I mean, Jones polynomial is relatively easy to compute with Kaufman bracket. All these others are doable, so these are just simple extensions. Maybe K models are a little bit more complicated. You have maybe to add cables or some Jones-Wenzel polynomials. So if you're a pure mathematician, then you can do that. Of course, it's painful, but in principle, you can compute any of these polynomials, of course, well, there is, of course, limit on patience and energy and computers, but they are, how to say, they are very explicit and computable in that case. In principle, for any R. Of course, in practice, it's very hard. Nevertheless, they have a lot of nice properties. So yeah, maybe it's a good time just to say some nice example. So, like if we think about example of a trefoil, trefoil not. So I mean, there is also a game between reduced and unreduced. Let me prefer reduced one. So reduced version when the value for the unknot is just 1. In reduced version, I think the original Jones polynomial. So Jones, maybe I could put it. So Jones, which is again SL2 and first symmetric, so it's just Jones, is equal to q squared plus q6 minus q8. At least in some normalization. Hopefully PT, it's 3 terms. Hopefully PT is, I think, again, in this normalization is a squared q minus 2 plus a squared q squared minus a to the 4th. It has this size, so 3 summons, but that goes, they're more complicated. For example, colored Jones polynomial, if you look at SL2 and then second symmetric. Make any stupidity. Oh, let me try just to write down. This has 7 terms. So they get bigger, but very computable. In any case, there are computer programs that can compute them, and so on. So they're nice explicit formulas and very nice invariants, so you can read off many from it. So what happens here, why they are nice? So on one hand, polynomial invariants are nice, just summing or something, not doing. There is no homology. I will not say anything about homology now, but you might lose a lot of stuff. So because when you set, for example, a equal q squared, because you have plus and minus, some terms can cancel in general. It's very hard to predict what goes with dimension. For example, here I have 3 terms, and then second symmetric is 7. So it looks, well, many things should and can and will cancel in terms of polynomials. So only later, at some higher level, some things will be nicer. So in homology, nicer, but nevertheless, this is a nice story. And there is one famous. So let me go here just. One famous also result is, and it's about, so if we just focus on, well, first was originally for colored Jones polynomials. So these are these polynomials, so we can look at the collection, so which is infinite collection of polynomials, SL2 and symmetric R of K. So for a given knot, this is an infinite collection of polynomials, but although it's infinite, it's a famous result that there is only finitely many of them are independent. So, and the claim is there is a recursion relation. There is a finite recursion relation for these polynomials, for is equal to SR. So in fact, although we have infinitely many, a priori one can say, we have infinitely many polynomials and different variables, different invariants, only finitely many of them are independent. All others can be determined later. For example, for Jones, color Jones for the trefoil, this recursion relation is of length 3, so basically I think it's a little bit complicated, but something like J SL2 SR plus 2 is a linear combination, but the coefficients are a little bit tricky. So it can be written as linear combination of the previous ones. So in some sense, something is going on in the background. So there is this finite recursion relation, also called, well, because it's not constant, also called holonomicity in math terms. I think the first one, I think the Stavros was the first one that showed this. There are also many famous things which all go in behind. And so I've not any mentioned this, but this in fact shows up in all this story and or later AJ conjectures and other stuff. And the same way as it happens for the Jones polynomials, called Jones, it was later showed so maybe here there is also theorem that even these invariants, so PR of AQ, so colored Honfley PT polynomials, so these big ones, they also satisfy recursion relation. So they're also holonomic, if you want. So even though there are in principle infinitely many of them, and well, they get bigger and bigger, exponentially, even super exponentially, they can be determined from the just first couple of them. And that is maybe important stuff. That's why all this story is interesting. I'll not say much more about this. I'm not planning now, but in some sense, this is also will be hidden in this Knots-quivers correspondence. And maybe Piotr was speaking about super A polynomials and other stuff, but this is more or less well, the background. So these are the main ingredients. So these polynomials and the fact that there is something going on between them. So I didn't show here any computations and any relations, but there will be opportunity at the end. So okay, these are the main ingredients. I didn't go in any details, and I suppose that you had, even if you don't know, you had some talks about this. And now finally, I'm coming to this Knots-quivers correspondence. And what was the motivation? So there are different motivations, but one of them was famous LMOV conjecture. So that physics kicks in many times in this story and throughout the last couple of decades. And LMOV conjectures say something, well, it's more general, but for now on it says something about these polynomials. So in a way, it says, of course, as I said, in principle you can compute any of these ones, and in principle there is some recursion relation which is complicated. Also, I haven't said anything about the length of this recursion relation. So the theorem is proved through some R matrix and other stuff, but there is a bound, so there is a finite. So the theorem says that there is a finite recursion relation, but it is how long it is. Well, the theorem gives some high exponential bound, but in practice they're rather short. So usually, well, you can make it short, so there are not too many of them. So in some sense there is only first couple of them, or some of them are important. Now it's question is how much. But then LMOV conjecture says something else. So yeah, it's complicated, but nevertheless, try to look at this series. So X is variable, so A and Q are okay, parameters, but for any knot, I put like this. So define this colored Honfley PT series. So arrange all these polynomials, all these colored so these are colored Honfley PT polynomials, so our main stars. Arrange them in a in some dummy generating series. So again, in principle computable, but in practice very hard. But then what LMOV conjecture says, okay, great, but then there is some reasoning. Let me try to write it. Never mind, I'll write in 2 steps. So the first original was like it's exponential of. So you want to rearrange all this sum in this following way. So it's a double sum. R and R larger equal than 1. So 1 over R. And then there is some auxiliary function fr of an qn x to the rn, where fr, so these are almost polynomials, so there is something I haven't said here. So there are some coefficients, n, r, I, j, some polynomial in 2 variables, and you have to divide them. Q minus Q inverse, this is coming from the value of the unknown in the reduced case. So basically it says, so this is the insight, Stida Marina and Guri Wafa invariant, so for physicists might be easier to understand why, but so I think the goal here is, well, re-express this in terms of these guys. And here, in some sense, you repackaged all the information, so all these polynomials, the knowledge of all these polynomials is repackaged in these numbers, in these coefficients, n, r, I, j. Now, I know originally, you know why formally it's written like exponential, but maybe I'll try to go further. And because it's exponential of some sum, and there is some x to the n over n, so it's some logarithm. So this will be some product, and the product at the end, this can be, well, this is just rewriting of, this is infinite product, or PR, IJ, and there is some extra summation. 0. 1 minus a to the I, q to the 2j plus 1 plus 2l, x to the r, and then these exponents show up, this n, r, I, j, again, the main stars, so these are just the numbers. So LMOV conjecture says, okay, you pick this up, all these, and repackage them in this way. Okay, so you rewrite infinite sum as an infinite product, and so LMOV is again a bit more general, but here we focus only on, so here we focus, so these are again just as-symmetric colored Hopefully PT polynomials. So these are again, as I said, our stars. And we repackage them in this way. So again, just look at it, be careful that here we have sum over all colors, so we have sum over all R's, but when you repackage, you will get again infinite product. But in order to get these numbers, so although we have n, R, I, J, in principle, they are not related to the single PR. They depend on all collections. So there is, well, yeah, you mix everything up, but then you spill something out. And LMOV conjecture, so what you can get from here, because these are, at least reduced versions, have integral coefficients, which is important. What is, well, okay, this is not, so the original, what one can show easily that n, r, I, j are rational numbers, and this follows quite easily. One can re-express them in terms of coefficients here. But the conjecture says that these are integers, so again, important stuff require exclamation marks. So the conjecture, so these, I mean, similar like polynomials, you have infinitely many of them, but they are finite, they are polynomials. Here also, there are only finitely many non-zero n, r, I, j for any fixed r, so it's similar like polynomial. And here they say they are integers, so physically, I mean, they're called BPS numbers, so they count certain particles. So for physicists or for mathematicians, they should be dimension of something, and they're integers because it's, well, physically it has to do with supersymmetric theory, so it's bosonic fermionic, and so mathematically, well, hopefully Knots-quivers correspondence show up why it is so. And the main reason is, although now it's well, it's polemical whether this is proved or not. Our main goal, one of the goals, we wanted to understand why these numbers are integers and can we count them or what they count, and somehow relate to this structure of these polynomials. And in order to do that, well, it was more of an accident at some point, and to realize that it's related to something with quiver invariance, and to that end, so I want to leave this for now at the table, exactly here. This part is seen, can be seen. So here we are purely on Knots side, and we want to relate it with quivers. So quivers, these are just, for us, these are just oriented graphs. And they can have multiple edges, they can have self-loops, it doesn't matter. And for our purposes, and it's perfectly enough to have only symmetric quivers. Meaning that there is the same number of arrows going from one vertex to another as it goes back. So for example, if we have two vertices, we have an arrow here and arrow back, and then arrow here. So these are like symmetric ones, and to each of them we can associate a matrix, which would be like adjacency matrix, which is just saying, so the matrix is of the size of the number of vertices. This one has two vertices, and you just count how many edges go from one to another. So here from first to first there are no edges, from first to second there are one, and here is one, and here there is one self-loop. So for example, this is like, if this is a quiver, this is the matrix quiver. And, or if you want, this is just some symmetric integral matrix, finite symmetric integral matrix. And then there is something, well, there is a lot about quivers representation, in theory of representation of quivers. There's some moduli spaces, and well, it goes much beyond this and even my knowledge. But the point is that it's not to mess up with notation. There is something that you can associate in the theory, which is called quiver generating series. So again, this is completely independent of knots. And so here the difference is this, something that depends on knots, or basically on this matrix. Now this generating series has as many variables. So they have, so if a quiver has, so if Q has k vertices, and this is what, for example here, two vertex. So we have each vertex receives extra variable, summation variable, and the summation goes like, so you sum over all, sum. So it's infinite series, so these are parameters bigger or equal than 0, and then it's minus q elevated to sum over all I and j, and then there is a quadratic form with this matrix C, and then you multiply it by, so these variables, and you divide, so Q-Pohammer symbols show up a lot, but it's expected. So, how to put it? Maybe this contains information that is relevant to the representation of quivers, and where you see it, this quadratic form depending on the matrix of the quiver. And well, finally, so there is again independent stuff. Luckily, so it's maybe not Kokiewicz and Soipel, but maybe other people in the meantime. And well, they did something called motivic, find something motivic Donaldson-Thomas invariants, which are again done in much higher generality. But in a simple case of symmetric quivers, they basically say that this generating series, so if we have a symmetric quiver, then this series can be repackaged in, again, so this was infinite sum, and this can be repackaged as a product. Again, now this now we have as many variables as summation indices as there are vertices, and then there is a big product. So extra j from C. So, okay. So you can repackage this in this way. Q to j plus 2k plus 1. And then you elevate to the exponential here. So there you have an exponent, there is some minus sign, but for us it doesn't matter. And then there are some these numbers omega, depending on the i's and extra parameter j. And so these are these dt invariants. So these numbers are dt invariants. Of a quiver. No. And so again, what is here, it's striking resemblance of the same situation. So here in the knot case, we had some infinite, we started with from some generating series, and the repackaged as some product. So who wants here can realize some infinite Q-Po hammers. But anyway, the numbers here are these exponents. And here, for somehow in a quiver's case, and in this very special case, you have again big, just some. You have some infinite sum, so some big series related to this knot. And then there is a theory which says, okay, let me repackage this as an infinite product with some exponents. And basically you say, okay, these motivity invariants are related. Oh, so this is the way how to repackage this information about this matrix in these numbers. And here now, in this theory, we have a theorem. So this is now important stuff. And so it was. So Kontsevich and Seidelman showed so that these numbers, so omega d1, so all of these dk j, so already Kontsevich showed that they are integers, so no, it's theorem. But they conjectured that they are also even non-negative integers, or natural numbers, and this was shown immediately later by Efimov, 2011 maybe. Essentially it proves that there is something associated, some algebra associated with it which is free, and then these are just dimensions. But again, there is fancy stuff, and there are some, you can express this in terms of different intersection cohomologies or some show numbers. There is some nice geometric approaches, but the point is that this is a theorem, so let me stress this if not enough. So here we know that this is a theorem, and now, well, you see, we want just somehow to match these two stuff. So maybe I'm now trying to write this as explicit as possible, or maybe as historic as possible, as we were, and it's a bit naive. So there are two different instances of the same procedure. So you have some collection of some invariants or some number, some series, which you can re-express as infinite products with some exponents. And somehow the things match, and on one hand you have some conjecture saying that some numbers are integers, and on the other, in other world you have it's a theorem. So what would be ideal, of course, to match this stuff, so somehow to use this to use this knowledge, and that's more or less what Knots-quivers correspondence. So let me not repeat. So Knots-quivers correspondence original statement, and this was by two Piotr's that we are here, and so we have physicists, we have myself, I would say more mathematician, and we have Reinecke, who is well, quiver representation guy, and so we want, well, our goal is somehow to match these things. So the main thing, the best would be if we can match the original generating series. So the original statement was for every knot, Okay, there is a quiver. Q, well, there is a symmetric quiver, such that the generating series, so which I called PK, X, generating series of knot, matches this generating series of a quiver. So the other guy here, which we call, oh, maybe it's C. So this guy here, the only difference is this guy's on this side here, X1 and XK. So the main, we have to specialize something, and what was relatively clear at the beginning. Well, you have up to some multiple depending on some numbers, Qi and times X. So in some sense, essentially, just emphasize here these two. My left hand writing, I don't know if it's seen. So that all these variables, you basically set them to be equal up to some overall constant, which takes care of this limit. So the goal was, so this was the original statement of Knots-quivers correspondence. This is still valid, of course, that we want to find for every knot a quiver such that this holds. In other words, this means that you can repackage. Maybe let me try to rewrite in more terms, which I hope better to use what I wrote here. So, in other words, maybe I'll keep it, but this is just rewriting this in terms of colored conflict PT polynomials. Basically, you want to rewrite PR of AQ, so for every, so that it is for every R, these colored conflict PT polynomials can be written as some sum over a couple of variables. We don't specify anything about this K. Then, so that there is some this quadratic term Cij. So the point is that there is a quadratic exponential in Q, and then some linear terms in A, so there. But these are not so crucial. And you divide everything here, this product. So in a more in the driest form, this is what you want. So somehow the statement is that you can rewrite every so PR in this way. And so the only dependence in R is here. So this matrix is some finite matrix. It's independent of R. So you have some. So if you remember for the, well, I haven't shown, but I'll show now some example. So that all information about PR, so that in some sense all PRs can be computed from integral symmetric matrix matrix C, which is some finite matrix. Well, plus there are some coefficients here, A and Q, plus, well, let's say just some integer, some, but this is just a few data, and well, it's relatively easy to see what it is. It can be seen from the conflict PT polynomial ordinary. But the main thing is here that it is quadratic. It doesn't go further than that. It can be repackaged. So yeah, I don't say what is K, but I mean this can be restated in this way for us. Again, some nice examples are in. I already mentioned the trefoil, and so famously, and what we use is that the quiver that works. So at least that this can be true is the quiver with 3 vertices. No here, but so it has here, as I said, it must be symmetric. And here we have 2 of them. And there are self loops, so here are 2, and here there are 3. So what this means that, so if we have a trefoil, and we can, so for it is even known these numbers, it is polynomials, you can compute them, and you can repackage that in this way, where C is the matrix of this quiver. So this is quiver, it's matrix. So, right, so it's 0, 2, and 3, since these are the numbers of loops, and then just the number of edges going from A to J. So in some sense, all, and I said these colored Hopf-Lipiti polynomials are complicated objects, and you have infinitely many of them, but in some sense, you can read off all of them just from a single small matrix. That's maybe, at least to me, that's one of the upshots. So if you're still sleepy, I have a question is, do you see something? So do you see why this quiver would be associated to this knot in any way? If you have an idea, we will be very happy to learn, because we don't know essentially how this works. So this is a pretty dumb way to compute quivers, and there are some explanations, and some work also by Kucharski. I think Pietro, I know he was speaking about this problem. So some other interpretations of this. So what is missing in this is their good definition and the right way to see this. But there are some observations that we could learn from this. So one of them is, what is the number of generators, or at least what happens with these diagonal entries or self-loops. And it turns out, in this case, pretty spectacularly, that in some sense, at least here, this is a reduced version, but think about, so again, I recall I never said homology till now, but even if you look about, if you remember what was the polynomials, so even the uncolored, so the original colored the original uncolored Hopf-Lipiti polynomial, or even Jones polynomial, had 3 terms. Mention this again, and even Jones polynomial was even simpler. But I think yesterday we heard Maritania showed even explicitly the homology, so the Kovanov homology, so that was unreduced but reduced homology. So Kovanov homology, now it depends on Q and T. So it will have, so this, there is a generator with Q degree Q squared, but which is in homological degree 0. And because this is positive knot, there is nothing in T degree 1, but here we have something in degree 2 and something in degree 3. So there is, and this is what we first realized, but then even proved for many of them, is that in some sense these generators, so these vertices are related bijectively to the generators of the homology. In this case it's simple, so you can take only Kovanov ones, and the number of self loops or the diagonal entries of the matrix are precisely the homological degrees. It was pretty surprising, so we didn't enforce this in any way, but this is what happens. Just I don't have too much time, and I just mentioned a couple of problems. So one of the issues, and maybe this was mentioned here, about this is that in some weird way we have some, it's not a map, but if we have knots and we have all quivers, in some sense we want for each knot we associate some quiver. Well, at least that's what Knots-quivers correspondence is saying. But there is something about this map. So first, if you use this definition as we are using here, there might be different quivers corresponding to the same knot. So it's not really a function, but it's not even one-to-one in any way. But there are different reasons. So you can have bigger quivers with some dummy variables, some overall summations, but you can also have quivers with the same size, so same number of generators or same number of vertices, but with some discrete operations. So some arrows might go around. But what turns out in that case, the diagonal entries are still the same. So somehow this homology sticks in it. But that's very interesting stuff, and there are a lot of work here, especially with Polish group. And there is also so only some set of quivers will enter. So not all quivers will show up. So, and that's an interesting thing what describes quivers, which can be or which cannot be related to quivers. Of course, in the meantime, a lot of computations have been done for many large classes of knots, and all these things works, even for rational and arborescent, even pretzel knots, and some of them more or less explicit, but at least proving this stuff. One small corollary, which I haven't mentioned here, is so corollary of Knots-quivers correspondence is that these numbers NRIJ, so LMOV numbers, because they are here somehow exponents, and these numbers here are exponents, and since here we have more variables, so these NRIJ, they are integral linear combinations of these omegas. So corollary is wherever a knot satisfies Knots-quivers correspondence, then because these numbers are non-negative, LMOV holds. And even more importantly, here we have some nice stratification because we have here many more variables. You have, well, additional stratifications by integers or by non-negative integers. So you don't just understand these numbers, but you can understand each blocks, how they are built. So there you have extra information in it, and maybe last 10 minutes I will have something to say about this. There is one additional question. So all this was done originally for colored Hopfli PT polynomials, but it can be done for other knot invariants. Maybe Sankyuk will speak about that, but there are other invariants like this FK invariant, FK invariant, which is related to this Z hat, which is three-manifold invariant of a knot complement. And so there was a lot of things that have been done there, especially Piotr Koczerski and Sankyuk, I think Park, he extended this for also, these are famous invariants by Gukov and Manolescu. But these invariants are also, they naturally have a series depending on X, and that thing can also be rewritten in, at least in computations that we have written in quiver form. So a lot of that. And maybe two lessons. So there are other knot invariants which can be written in this way. So maybe Knots-quivers correspondence is much more general in some sense, but in some sense, this dependence on a quiver or on a quadratic exponent is what is important and what one can read off from all this. And there are a couple of lessons from this, at least to me. So one of them here, in this case, when it's written in a quiver form, meaning that there is a quiver which after some specializations can be written. So here you were forced from the very beginning to have, well, here there is some lack of symmetry, so A can go with some powers, Q can go with some powers, but X originally was only with one. And here I will emphasize that, well, why not even here, we should be more open conditions. Why can't we add one extra data here with X? So this is what is needed in order this to work. But also it was needed, there are knots, well, relatively complicated ones, already 42 or some of them, which were very tricky to find these quivers. And there are some reasons, which is a lack of exponential growth. So there is some super exponential growth, and which can be explained only with adding higher degrees. And also, again, by Piotr and Pietro Longhi and Ekholm, you have the same, so more symplectic geometry explanation or more physical explanation through count of holomorphic disks, where also you're naturally forced to add these higher level generators. So you're allowed, but you're forced to add higher ones. And what I can say that I now believe that this is the right framing, right formulation, and that you don't even need to, well, NI's don't need to be all one, but you don't need to go much higher So I will not show how it goes, but maybe a slide that doesn't matter. So example, the weird example is like 942, and that is my flagship example. It's a recent paper from February where I computed the quiver for this one, and this is a big one, so you need. Well, so the quiver is something like 33 by 33, but you need only first level, and I is 1, and there are 9 of them, and I is 2, or remaining 24. But basically that's it. So from this information, for this very, very weird knot, lovers of knot theory know that this is very weird. And well, for me it struggled for a long time. But with this you can plug in and it works. So well, it's a big, there is a lot of structure here, of course. But so I think the right formulation of Knots-quivers correspondence, which is of course still in its whole generality conjecture, is that probably we should certainly allow higher degrees, but these degrees doesn't need to be very big. So this has to do with these recursions. So we don't need too big of a recursion. In some sense, even for complicated knots, we don't need to go very high. And in some sense, all the information about all colored conflict polynomials of 942 is in some sense hidden here. By the way, these homologies still show up, even the second colored homologies. So this story that homologies are entering here is still inside. So there is a, well,
so there will be 33 diagonal elements for the 9.
33 diagonal elements, yeah. So it's very big, but very nice. Very structural in some sense. But the point is you don't need to go much higher. Okay, seems, I don't know if I have 45 minutes or 1 hour now.
It's just 1 hour, but including some questions.
Yeah. Okay, I'll just show some combinatorics hidden in behind of this. So maybe part of generalization from title was both relating to these invariants, which is still, I mean, which can be still better understood and it's famous. And the thing is that I think this should be the right framework, and all the story LMOV still holds sterile integral combinations. Well, again, still everything holds. All these properties are holding. All these issues with, say, uniqueness.
It will also be 0.
It will be 0, yeah, as well. So here I think we don't need it, but here you need 0, for example, for FK. I think even for the trefoil or something. But it can be 0, yeah. That's fine. For 0. For very brief combinatorics, I have slides maybe. Let's continue in this world. So we have this colored conflict, PT series, and we have this related, if you want, this quiver one. So in a way, in a process when you want to compute, imagine that you really want to compute these numbers from this series, well, there are various reasons, but also some recursions, but if you want to compute them, it's natural to observe. So maybe, I don't know, try this, so maybe P bar, let's say, of this quiver, X. Well, I'll lose some details here because it doesn't matter. In some sense, again, you set all xi's to be x, maybe with some up to some multiplication, but I still keep x for now. And you can look at the quotients. You can look at the quotient of the form qx divided by q minus 1 to the x of this series, and that's some epsilon of x depending on q. And you can write this as a sum, again, as a series, because this was a series in x, and this will have some coefficients. And you can also take limits. So well, now, after dividing, and then you can take limit q go to 1 of this quotient. And so it turns out that these coefficients here, both this and this, have very nice combinatorial interpretation, explicitly and very explicit in some special cases. So, and in particular, in the case of torus knots. So if I have like RS torus knot, you can perform all this trickery, and you can get its quiver and its corresponding matrix or Q. We did it for some R and S, not just even framed R not as fine when R is equal to 1 or something like that. And if you perform all these stories, somehow these numbers AN, even they will count something, and they will count something very interesting. And this is so you plug this line of the slope R over S, so these are torus knots, so they should be mutually prime. And you count the number of lattice paths from 0, so here is 0, and there is some point on it, so let's say some SK, RK, some integral point, and then there are many lattice paths, and you can count all of them. And somehow surprisingly, AN is exactly this count, so AN's count up to some minor modifications. They count lattice paths. So it's a very non-trivial combinatorial problem. And notice that it counts because it naturally stratifies through this, and you can use now quivers. You get very nice expressions, of which some will reprove some famous ones from the combinatorics. There is some called Duhon paths, which is the same for 2-3 line. It's a famous result in combinatorics. And what you naturally get from the quiver that corresponds to a trefoil, because this is, so it corresponds to 2-3 torus knot. You naturally, you really arrive at this formula. So, and this well, at least to me, it's a great surprise, because it's something you don't even hope for, but then you get something purely combinatorial. Also, in the other way around, somehow it seems that from the count of Duhon paths, you can go around and somehow get a lot of information about colored polynomials of TRS. And this is, so here I'm lying a little bit. So for this, you don't even need the whole TRS. So if you remember, this depends on A and Q, because these are colored polynomials. For this count, you can set A equals 0. So you only need just a piece of this. So it's called bottom row that we call it. But if you use the full, this is so okay. So this is Spantel and also with Piotr. No, this is many years now. Not count. No, this in the middle. But this has been around for a while, but I think this one is if you use the full, so if you use TRS and use PR of AQ, so in 2 variables, and then you have much more information, then what you will count at the end, so is again the same slope, and then you have lattice paths, but you also allow diagonal steps. So usually these are called Schröder paths. If the line is y equal to x, so if it's the real diagonal, but here we call it generalized Schröder paths. So these are the lattice paths where you go up and down and also diagonally. And if you count, so these ANs in that case will depend on A, and somehow powers of A count the number of diagonal steps. So precisely when you don't have A, you don't have diagonal steps, as here. And in some sense, this is very rich combinatorially, and it keeps information. So I'm lying a little bit, not about this, but about homology of this. So it's very. So I'm going a little bit in advance. So in a couple of days, this will be on the archive, I hope. This is also with Piotr, and there are also nice details here. But so again, you can get them, and you can obtain either through quivers or directly from the paths. And the very last moment, and because I want also to mention one final thing which is related to this extra parameter, so in generalized. So here I specified all xi's to go to x. So for this combinatorics, although very rich, it was perfectly enough, the old stuff. So the question was when, well, now we have this generalized Knots-quivers correspondence. So what will happen if you do, well, the same stuff? It's not much of an extension, but let's do this for the, when you have to set. So when you set xi and you, well, you allow that to go to x to the ni, so maybe higher power. And so this is joined with Dusan Georgievich, who's, I think he spoke a little bit about this in March, right? March was the first workshop. Yeah, I think he mentioned already this, and this should be also in a few days, hopefully on archive. But the point is here that you can play with this story, and then in that case, if you want the difference, you can also use the old stuff, and it's like changing here, instead of q to the 1, you go to q to the some other power. Let's say n. And in a very, very simple case, so if, on the not side, so for not, it's just framed unnot. Colored invariants are framed not invariants, so there is some dependence on nothing. And so if you think about some not with framing, and so corresponding to it, a quiver is just a single vertex quiver with many loops, so let's say f loops. And if I say that this vertex has this level, well, let me put n, so not necessarily 1, and it can be bigger than 1, then miraculously these things also count something, and there are, well, you can even find nice expressions. So in all these old stories that we had, these lines were going through the origin, and here somehow what they are counting, and I'll just draw this critical line, is somewhat shifted, so it is, maybe in this notation it would be f minus 1x, but then it's shifted by n minus 1, so that is, if n is bigger than 1, you see it, so there is some offset here. But then still you can count lattice paths, and these are precisely counting these things. So adding this higher level still has the same combinatorial expression, just shifting it a little bit. Well, in this case, you can even count explicitly, and well, these numbers, they're, at least in classical, they have a closed form. So if this point is like, if x, if here is n, you can even count explicitly. It's like this. So the matrix of the quiver is just f, so somehow this f shows up here, and this n level shows up here. These are combinatorially can name array numbers, but we can rewrite them. And here there is some lack of symmetry because you have to go up. Here you can go above or below. Here you must be below, and this counts exactly this number of paths. So there are similar, very beautiful and very rich. So these numbers are very tricky stuff to compute. And here, not just that we relate them with, how to say, so you relate them with first with torus knots, and you can even read off torus knot invariants with some modifications. Plus, because you know quivers, you can, by this way, by setting this thing, and you can stratify and count them or refine these numbers. So it's literally like a refinement in physics or some categorification in mathematics. You can slide them and even count them. So this is the simplest case, but you can probably go. So this is some mixture that we mix all this stuff. So let me stop here. Thank you.
Can we give some insight on Kaufman's generation series, colored Kaufman?
Well, we can discuss later, but in my paper I did something for 942 for SO series. because then with this it matches something with SO3. So there might be some Kaufman. We discussed a long time ago. I have now the right formula. So in principle, this should be working, but I don't know. So this is. I don't know. So let me put like this. So it might be.
I'm looking at SO3 is all integer colors.
Yeah.
Sorry, even integer colors.
Yeah.
So it should work.
In principle, yes, but maybe it's a little bit more complicated. Maybe there is something. So I don't know. So I haven't done, but simply this Kaufman and SO family is much more complicated in some sense. I think that. So you have this
symmetric colors, but even symmetric colors is what I would have thought.
I know. Well, maybe this is speculation, but somehow I feel that SO2n and SO2n plus 1 series are going different, even in homology. So maybe some part of it would be as easy as this, but it shouldn't be too much different. I don't know. But I haven't done anything yet. We can discuss at some point, but yeah. This is part of so Knots-quivers. So I have on the Knots side, we are here really focusing on colored Hopfli PT, and maybe a little bit now on this FK. But this is what we understand best. But it can be, again, for anyone. And again, it would be great if you can pass from here to here in some more abstract way, rather than matching some series or. Again, any color.
So in this last example you mentioned, you see that for this F-loop quiver at the moment. Or other quivers as well, or this is like frame metal.
So yeah, that's frame metal. So I think I should double check everything. So this should work, I think, in the same way if you if all of vertices are of the same level. So if you take, like, I don't know, for the trefoil we had some 3x3 or 6x6 quiver. If all of them are of not level 1 but level 2 or level 3, then it will go up. So I think it's, well, that should be the correct. That should be correct.
But do you see that or?
Yeah. In the cases I checked, what I don't know is, for example, if one is of degree 1 and one of degree 2, so something. But yeah, I don't know the interpretation. But yeah.
For this example, can you have a bigger matrix so that all the n's are 1, like 55 by 55?
Sorry, so this is, for this example, so this is just an example of a knot which is famous. So here, well, you will have, you have something like 33 x's, and then for some of them you put x, and for other you put x squared.
Yeah. So my question is whether you can find another matrix that's bigger, like 55 by 55, so that all the n's are 1. So
yeah, so original. So there is still a possibility that this can be achieved by just x to 1 with bigger quiver, and that was what was our original goal. As stated, it's problem on polynomials, so it's perfectly legal to do that, and maybe right thing. Just, but there will be a lot of cancellations. The only thing is that, for me, is, as here, you expect some homology to run in the background, and if you have homology, you must have some generators. You cannot cancel generators just by I don't know. I mean, in polynomial, you have something plus and something minus, and it cancels. If you have homology, it's more complicated. So this seems a little bit, in this case, to me, it seems more natural. And maybe there are some reasons, other reasons that force, well, okay. I cannot say, prove, but I feel at least for this knot that this is the right choice. More natural. As I said, here there is a problem. For each knot you can associate many quivers. And especially if you now change, if you allow here something, it can be bigger, smaller. Usually there are a lot of cancellations. But if you expect and hope there is some homology going on between and some more rigid structure, then some of them are more natural. So one of the not so clear statements is that this might be more natural, but chosen wisely. Well, when I did some computations, even for small knots, I don't remember, even with 6 crossings, which are knots that are well behaved and like rational knots and everything. And you can see example of a quiver which has 1 and 2, and I have another example which is with 1. And for them, I think the 1 is more natural because of some homology reasons. So non-uniqueness can be very big.
So it's not true that in general you want your quiver to be as small as possible.
So yeah, so that's the reason why.
Yeah, but you said that there's another example where all the n's are 1.
But then that with 1 is smaller.
All the ones, all the n's are 1. That's also
Well, in that particular case, so
So in general, you want your matrix to be as small as possible.
yeah, but that's more, let's say, rule of thumb than rather. Because you can easily grow your quiver. There are many, well, even some dumb stabilization. You can add 2 rows and 2 columns. There are some general expansions which say that you can write 1 and in a different way. So you can grow always, and somehow it turns, well, it showed up till now that the smallest size is the right one, and usually it matches homology. So now homology, the problem is that I'm saying homology, it's not Kovanov homology, it's some conflict PT homology, or some colored conflict PT homology, which is a little bit shaky issue, but there is a story, structural story, which says how all this should interact with each other through some differentials. So hope is to be the quiver as small as possible.
That is
That's
main
not
hope, but
yeah.
the vertices of the quiver should be in one-to-one correspondence with generators of homology. And it's probably hard to make a quiver yet smaller than that way. But
So somehow this homology is giving you some bound on that, so let's say. But again, this showed up later, so when we, well, okay, we expected something like that, but not as explicit as here. So yeah, that would be the right formulation would be somehow to match quiver with the homology. But again,
I think we have to discuss in subgroups in next 5 quarters, and then at 1:30 we'll meet for the next.
I'm here 1 more week, and maybe
some more times.
there will be some serious next week.
I hope it's a baby.
Discussion, yeah.
You will have a lecture series.
Oh, okay, no, that's not a maybe, but if anyone wants, I'm here and around, so discuss all possibilities.